All right, so we spent kind of a whole unit looking at the properties of light, mainly the wave properties of light. Um, and so now we kind of really bring it home here. I just have this little bit here. Recall, right? The momentum of a photon was just h, which was Planck's constant over whatever the wavelength is. You can rearrange this and say, okay, yeah, for any photon, for any light wave, if you will, the wavelength then is just equal to this constant. Um, Divided by mv, or if you can rearrange it for that, um, or the momentum, which right you could write as mv, and it was Louis de Broglie in 1924. I think we were sort of leaving off in the last one about this time in history, eh? So he looked at that and said, well, yeah, like, this is here is for a photon, but it is a momentum. And so you could just write momentum as mv, which is the momentum of a matter particle. And you could figure out the wavelength, if you will, of a matter particle. And I think this was in his PhD thesis where he proposed this in 1924. There's a nice picture of him roughly around that time. And this is actually picked up by Einstein. He liked it, and wrote about it. And it was after that where Schrodinger saw that, loved the idea, presented it at a conference. Everybody was like, yeah, okay, yeah, that's nice, but you got a wave, you need a wave equation. And it was after that he developed Schrodinger's wave equation that you may have heard about. But the idea here was that matter could behave the same way as waves. Okay, so you may recall the Bohr model of the atom, where we sort of had these, orbitals, if you will, and each of these lines here sort of represent different energy levels, right? So you've got an electron, which typically will just stay in its lowest energy state, and then if it gets some energy from a photon or whatnot, it'll jump to a higher energy level, right? And these are discrete energy levels. We know that, and that was consistent with the photoelectric effect and everything. But yeah, so for de Broglie, it was, well, no, like they could actually, if you think of it kind of like a standing wave or something, right? These orbitals or whatever actually have to be such that whatever that electron is, right, you kind of have to imagine it having a whole number of wavelengths, right? So it's sort of like resonance or something like that. It can only have certain wavelengths or whatever. And then this one, it's sort of drawing just one of them, but you can imagine it could be others too. It could be, if that sort of represents this orbital, right, it could be, right, something, well, that's a terribly drawn one, but you can see how there's, this first one here might represent like a different frequency or whatever. And yeah, this turned out to sort of work. When we did experiments, I would draw you back to, remember when we looked at the double slit experiment, and we said, you could do that with light and it works, but we said if you did that with electrons or any particle, you get the same interference pattern, right? And so this seemed to be the explanation for that no matter, let me get rid of this, it just looks funny, I think that would just be confusing. But yeah, you could do this with anything. You could do this, you could figure out what the wavelength is for any particle, whether it's electrons or protons or whatever you want to do this with. If you've got some sort of beam over here, right, you've got your electron beam. And you're going to get that same interference pattern, which is kind of shown down here as well, no matter what you do it with. And that seems to be the idea that, well, all particles seem to have these wave-like properties, if you will. And what's really neat about this, or what I remember finding kind of strange about it, is you do this with electrons and then you say, okay, maybe this is something like maybe they're interfering with each other, right? Maybe this is weird, but okay. So you send the electrons at this apparatus one at a time, right? You could even do it over time. Every hour, I'm going to send one electron, right? And what you're still going to find is this same sort of interference pattern where you're going to have these positions on the screen, right, like this, where no electrons ever hit. Again, even if you send them one at a time, it's like somehow it's interfering with itself. And that's sort of, pretty good support, I suppose, for this idea that, yeah, like even any particle, really, it's hard to describe it as a particle, right? You kind of have to look at it more like a wave. So anyway, yeah, here's an example you can do with that. If you did this double slit experiment with electrons, as I said, I filled in everything today just to speed it along, but still consider, if you read the question, how would I solve this, take a second. So electrons are used in a double slit experiment. They're fired at two slits separated by 2.2 micrometers at a speed of 5 times 10 to the 4 meters per second. The distance from the slits is 3 meters. What's the separation between maxima on the screen? So basically, what are you solving for? And this is kind of good if I was in some kind of interview trying to explain this, or what am I solving for? I would say, well, here's a maxima on this screen, and here's another maxima, and so this is the distance I want here. Not M. Right? I want this distance between maxima. I want to figure out how far apart are these. And so I can go back to the equation that we used for double slit experiments. It was with light, but again, didn't really matter. Any wave. So that was, right, delta xm was L times lambda over D. A little bit of a small angle approximation here that sine theta equaled tan theta, but that generally works pretty well. And since we know lambda just from up above, lambda equals h over mv, we can sub that in for lambda up here, and that gives us this equation here, where delta xm equals L, the length between the slits in the screen, times h over dmv. And at this point, yeah, it's sort of just plug and chug, put in the numbers, which I do, and you get a number here that's about 2 centimeters. But that, yeah, the larger point I would say is, like, even if you want to go back up here, you want to look at a photon. It's like, well, okay, yeah, it's a wave, right? But it's also a particle, and that's sort of, like I said, how I look at it. Like, it is a particle. It's a photon, if you will, if you want to think of it that way. And if you remember at the beginning of that, I was like, okay, here's my photon, and as it's moving, right, it just has, these wave-like properties, that it's got some sort of electric field, right, that's fluctuating and changing as this thing moves through space. And that seems to be true of all particles, that whatever, they just sort of have these fluctuating fields as they move through space. So what is actually happening here? Let me be very clear. The results in how to do quantum mechanics is very well established. I think quantum mechanics and this idea of wave-particle duality, probably the most well-tested theory in history, right? So and physicists are very in agreement about how to do quantum mechanics, how to use these equations and make these predictions. And as I said, yeah, you get some weird results. You get some spots like this again. Even if you send electrons through one at a time, you know, it's weird. It's like somehow the electron, you've got to believe, right? It's like you got to believe the electron knows, or somehow, like, you would think an electron would either go through this slit or that slit, right? A single electron. Like, now what's neat about this is, even if you do this with electrons and you put a detector on one of the slits, right? You say, okay, I'm going to put a detector here, right? What happens? You just want to know if it went through that slit or it went through the other slit. That ruins the experiment. You do not get the interference pattern anymore. Right? Which to me is almost like, okay, it's like somehow the electron knows it's being detected. That, like, is human ignorance a part of this? Like, as long as you don't know which slit it went through, you get this interference pattern. You get these dark fringes here where no electrons ever hit there. But as soon as you put a detector or do anything to figure out which slit it goes through, all bets are off, and you just get, you ruin this interference pattern. So that seems, really bizarre. Again, you can do the predictions, you can use these equations and others, and get answers, and all that works. But what does this all mean, right? What's really happening here? How does the electron, like, know that both of these slits are open and it's not being detected, right? How do you interpret that? So there were several different interpretations. One is sort of this collapse interpretation. The idea, took some visuals out of the textbook here, basically. Uh, the idea is that, well, electrons or any particles can be either, right? They can be particles or waves, but it's either one or the other, right? So the electron is a particle. While it's here, in this gun that's going to shoot the electrons or whatnot, and then as it moves through space, okay, now it becomes a wave. And then once it hits this detector over here, okay, now it turns back into a particle, right? Um, yeah, not very interesting, I suppose, or whatnot. It just sort of says, well, it is what it is. Let's just do the math and not really worry about it. Let's allow it to be either. This pilot wave idea is a little step along the weirdness train. But the idea is there is this sort of mysterious pilot wave that is everywhere and knows everything, and somehow controls everything in the universe, and it understands even all future events. And so, in that sense, the wave knows when one or two slits are open and if a detector is turned on. So it's kind of, again, I really think that part mysterious is there, that it's just sort of this pilot wave that permeates everything and knows everything, and not very rich and not much you can really know about it, but okay, there's an idea. And then you can see here the electron just sort of is influenced by this, this other thing, this pilot wave. Probably the most popular interpretation of quantum mechanics was known as the Copenhagen interpretation. So that's where they were when they formulated this idea. And this really just takes the math pretty seriously. It says, well, like, the physical world is just like the mathematical world. What we know, if you're gonna, look at, like, something like an electron and where it is in space or whatnot, well, actually, mathematically anyway, it's in a superposition, right? So you could say we had for light, we just had single waves, but typically you would have multiple waves. So you'd actually have a space like this sort of represented by some sort of wave equation. And you'd say, well, it's, it could be like this. And I mean by waves, we're just talking about typical sine and cosine functions, but you can add them together and say, well, it could be any of these functions at this point in time. And so you're saying, well, it's in this superposition. It's, you know, it's neither, the electron is neither here at A or here at B. It's just anywhere in this space. And that's just how it exists. It's not really a particle at a single point. It's just sort of, anywhere. That's how it exists. And then if you take a measurement, yeah, okay, it collapses and ruins it, but it's before that it really does exist simultaneously in these different states. And the probably example you heard about that, which was actually sort of presented as a knock on this was, but Bohr said, well, yeah, oh, okay, yeah, that works fine. And this idea of Schrodinger's cat was, well, okay, so if you're saying that everything's in a superposition of states, then this ends up looking a little more like a Rube Goldberg machine or something. There's a lot to this, but at the end of the day, the point was to say, look, that means this ridiculous situation is both. So the idea is you've got like some radioactive material that, let's say, there's a 50% chance that it's going to radiate at any particular moment in time. You don't know, so you just say, well, it could be either. If this radiates, then you've got your little Geiger counter here, detector, which will make a noise, which will disturb the string here against the scissors, so they'll cut that, which will make the hammer fall down and smash the poison, killing the cat. So if you don't know if the radioactive material has actually radiated, and you say, well, it's in a superposition of states, right? It either has or hasn't radiated. We don't know until we take a measurement. Then it either has radiated or it hasn't, but until then it's both. So that means in this sense the cat is both dead and alive. You can't say that. Which, and again, they said, yeah, okay, that's what that means, but okay. That's what the math says, and that sort of works, right? And then the next level, which is, was more science fiction in the 20th century, but it's really gaining more popularity now because we're sort of like, yeah, I mean, these ridiculous things or these wild ideas could actually work, is this many worlds idea, which states that parallel universes exist for each possible state. So if you do take some sort of measurement or whatnot, it's not that, the wave function actually collapses or what, it's just the universe separates. You've got two different possibilities. As mentioned, science fiction loves this because it's, you can say, oh no, there's these alternate universes and maybe somehow you could connect to them or get to them where these other things that, could have happened did happen. There's another universe where you didn't take physics in summer school and you're sitting, relaxing, enjoying your summer or something. Right? So, similar to the Copenhagen interpretation, the cat is both dead and alive, but now it just splits in two. So there's one universe where the cat's dead, another one where it's live. And again, this means you don't have to have this, collapse or whatever. Everything, the superposition is sort of preserved. Okay, last thing we got here, the uncertainty principle. You've probably heard of it. It's pretty popular. We're up to 1927 now. Heisenberg's uncertainty principle, to give him credit, states that there's a limit to how accurately simultaneous measurements of position and momentum of quantum objects can be. This is the equation of it right there, delta x times delta p. So delta x and delta p are these uncertainties, in delta x for position, delta p for momentum. So the product of these must be greater than h, Planck's constant, divided by 4 pi. Right? You cannot know this product with any more certainty than that. And it's worth noting that this has nothing to do with the limits of technology or measurement error, right? So this isn't like saying, well, in an experiment, humans could never know this that well, right? This is a fundamental law of nature. This is saying, no, it's actually impossible to know position and or momentum with any more certainty than this. And this really derives from the fact that, again, everything is really these, quote unquote particles are essentially waves or superpositions of waves, if you will. And so if you have, like, if you look at one single wave, right, if you represent a particle like this, and you've seen sine and cosine functions before, which is how you would write this, uh, this goes on forever, right? So if you were trying to say, no, I want to know, the exact momentum, let's say, of this or whatnot, um, right? Your position here is, well, you've just made this thing go on forever, right? You have no idea where this thing is. If you're saying, no, I have this one wave that represents this momentum, I know this exactly, um, then you couldn't state the position to any certainty at all. On the other side, if you want to try to localize something in terms of waves, you have to add more to it, right? So you could say, well, I've got one wave here, and then I add a second wave, or usually what you kind of do is add one that's just a little off. And then when you look at the superposition of these, you put more and more of these together, you can actually localize it and you can get kind of a superposition that looks essentially like that, right? And this is, you can say, oh, there's the particle, and the amplitudes here in some sense give you the probability that it's at that position in space and whatnot. So that's what you would have to do. But now you've added together so many different waves that, which one really represents the momentum, right? You've tried to localize this, but now you've got way too many waves. So which one would it actually go off on in terms of momentum? You couldn't say, right? So it's really just, I said, a fundamental law of nature. It's not in any way to say, we can't, we're just not that good. Here's an experiment. Like, I'm sorry, I don't have a better visual of this. I'll link a video or two in the course plan where you can actually see this kind of happening. We've looked at diffraction before, right, where you get a single slit. And so you've got, now you could do this with electrons, you can do this with light. Again, it's all waves. And you remember seeing this pattern when we had a single slit and whatnot, right? And so what happens if you actually narrow the slit, right? And for a little bit, right, you'll actually see it decrease. So I should mention, right, if you're narrowing this slit here for a bit, you'll actually see kind of a central bright spot getting a little bit more precise. But once you start to get to this sort of, range of uncertainty where that actually has to be a factor, then what you find is the central bright spot actually starts widening, right? And that's essentially because by narrowing this slit over here, what you're doing is you're having more certainty about the position. You're saying, well, I know that it has to be in this little area right here when it goes through here. That leads to more uncertainty about the momentum, which, along with, speed or whatever, also includes direction. So that means now it could be going, right, more here or here. You don't know, and that's just, again, that's the uncertainty principle at work. And so you end up with this wider central bright spot. Like I said, I'll put in some videos. It's pretty cool to actually see this, that as you narrow this, it starts to widen. One example here for this, I already put it in just to speed it along. An electron is confined within a region of width r equals 5.000 seems like one of those cases where, significant figure sort of matters a little bit. And this is roughly the Bohr radius, right? So this is roughly the radius of the atom, right? And so if you want to confine an electron to that sort of space, well, then estimate the uncertainty, and we'll just look at the x component of the electron's momentum, so we can deal with linear momentum. And then from there, we can determine the kinetic energy of an electron with this magnitude and momentum. So I'll go through it, but do take a second and think, yeah, how exactly would I solve this without looking at all the equations I have here? And then I'd say, okay, yeah, all I would essentially do here is take this equation, rearrange it for delta p, that's to say divide both sides by delta x. So this is going to give me the uncertainty, right, the delta p here for the momentum of this particle. Plug in the numbers, and I get a pretty small number, but one that we can notice in some ways. 1 times 10 to the negative 24 kilogram meters per second, right? So that's saying we cannot have any more precision than that in terms of the momentum of an electron. And one of the things that kind of comes up here is this actually has a little bit to do with like why the atom is the way it is, why the electrons have these large orbitals, and protons and neutrons have these really, really small, right, spaces that they seem to occupy, and that has something to do with uncertainty, right? Because they have, larger masses and whatnot, so you can confine them a little more. Anyway, taking that number, if I wanted to look at, what would the kinetic energy be of something with that momentum? In this case, this is low enough. I could just use classic kinetic energy equation. And because I have momentum, I can take this equation here and multiply the top and bottom by m, just so I get mv here, right? And mv then is just going to be momentum. Sub it in, and we know the mass of an electron, again, 9.11 times 10 to the negative 31, and that gives me a kinetic energy of 6.11 times 10 to the negative 19 joules, or if you prefer and are starting to get used to it, 3.81 electron volts.